Hey everybody. I want to spend a little time talking about the mechanical advantage of load blocks. We've already talked about load blocks and mechanical advantage. This is a review of what we've discussed in class. I do add a little additional information concerning friction loss and the friction loss factor. But again, more parts line, less force required on the lead line to move the load. That's the advantage of using a multiple part line load block. An example of the mechanical advantage would be with a 6-part line configuration. 6 parts of line will have a 6-to-1 ideal mechanical advantage. However, ideal mechanical advantage is just that. It's ideal, it's not real. In the real world, there will be friction involved, and that friction reduces the mechanical advantage. For each part of line, the friction loss increases and the mechanical advantage decreases. I mean, there still is a great advantage of using a multiple shiv, multiple part line load block, but it's not going to be ideal. 6-to-1 advantage with 6 parts line. It's not going to be 16-to-1 with 16 parts of line. Friction takes away some of that advantage. Just a small amount, but it is an amount that we need to consider. The net mechanical advantage, which is still going to be great, is the mechanical advantage when accounting for friction loss. And let's talk a little bit more about friction loss and the friction loss factor. Now, if there wasn't any friction, the load block would be 100% efficient. But again, that's not happening. Shivs are not 100% efficient. There will be friction loss for each of the shivs. And when I say each of the shivs, we're talking about each part of line in the block configuration. If the efficiency of a shiv is 97%, which is good, that's pretty common for a shiv efficiency. If it's 97%, that means 3% must be added to the force required to move the load. And again, just as another example of how friction increases a required force, let's say we're sliding a box across a smooth tile floor. That's going to require less force than sliding it across a rough surface like concrete or asphalt. And there's always going to be friction involved. What we do with load blocks and determining mechanical advantage accounts for that. Okay. If the force required to move the load without friction is 100%, the force required to move the load with friction is 103%. That's if it's 97%. So again, if 97% efficient means we must add 3% to the force required to move the load. Again, the force required to move the load with friction is 103%. When we convert that 103% to a decimal, 1.03, 1.03 is the friction loss factor. This friction loss factor is cumulative and must be computed for each shiv, each part of line. All right, hopefully that gives you a little bit more understanding of where that friction loss factor comes from. Let's go ahead and look at a sample problem. And again, there are 2 ways of coming up with the answer for this type of problem in this type of situation. We'll look at both methods. The first method is the long method. We divide the load weight by the number of parts of line, which is also the number of shivs. This gives the force per line before accounting for friction. We've got a 98,000 pound load. We've got an efficiency of 97% with 3% friction loss. And we've got 6 parts of line. So we take 98,000, divide it by the 6 parts of line. That's the force that would be required on the lead line, on the pulling line, if there wasn't any friction. But we've got to account for the friction. There are 6 parts of line in the problem. This method requires multiplying the friction loss factor by the force per line value 6 times. For line 1, we take 16 16,333.33 and multiply it by the friction loss factor of 1.03. And again, the 1.03, like we illustrated on the previous slide, is derived from the shivs being 97% efficient. If the shivs were 95% efficient, the loss factor would be 1.05. But again, we're at 97%, so it's 1.03. For line 1, we come up with 16,823.33. Now for line 2, our starting point is 16,823.33 times 1.03 equals 17,328.03. Again, this is done progressively, line to line, shiv to shiv, all the way through the 6 lines. For line 3, we start with 17,328, multiply that times 1.03. For line 4, we start with 17,847.87, multiply that times 1.03, we end up with 18,383.31, line 5, and line 6 until we get to the very end. Line 6, that's the last line, and this is the force required to move the 98,000 pound load, 19,502.85 pounds. Again, this illustrates, the way we did this illustrates how a little more force is added for each line due to the additional force required for the line to overcome the friction of the bearings turning inside the shiv and the rope bending over the shivs. But there is a shorter method. And like I said in class, I'll mention it again, crane operators, if they're taking the certification exam and they have a problem like this, they are pretty much stuck doing it this way, the long form method, where line by line all the way till they get to the end. They have to do it this way because they're not allowed to use a calculator that will do exponents. But if you're taking the CSP exam, or if you're doing this in a real lift planning situation, you're helping the engineers plan a lift, you can use the shortcut method because you're not limited on the type of calculator that you can use. You've got to have a calculator that can do exponents before you can use the shortcut method. And this method accounts for friction loss by multiplying the per line force by the efficiency to the nth power. What do we mean by that? We have our per line force multiplied by our friction loss factor, 1.03, and we take it, in this case, to the 6th power because there's 6 parts line. If there are 8 parts line, it would be 8. So once we have all this squared away, all we need to do is this calculation, 16,333.33 times 1.03 to the 6th power, and there's our answer. Same as we get using the long method. 19,502.85 pounds are required to move that 98,000 pound load. All right, let's go ahead and do another example problem. We have a crane reeved with 4 parts of line. What is the amount of force on the lead line required to move a 50,000 pound load? Assume a shiv bearing efficiency of 95%. It gives us a 5% friction loss. Remember, the lead line is the line that the pulling force of the hoist is exerted upon. Or if it was a block and tackle, the lead line, if it was a block and tackle manually powered, the lead line would be the line pulled by the worker pulling on the lead line. All right, well, let's go ahead and take a look at this. Again, our efficiency's a little different than we had with the previous problem, but everything else is exactly the same method. We divide the load weight by the number of parts of line. This gives us the force per line before we account for friction. 50,000 divided by 4 parts line is 12,500. Again, if there wasn't any friction, this would be the force required to move the 50,000, but we've got to account for friction. To account for friction, we multiply each line, or the individual line load for each line by 1.05. Again, it's progressive, it's cumulative. 12,500 times 1.05 is 13,125. For line 2, we start with 13,125 multiplied times 1.05, 13,781.25, and we do that for all 4 lines. And when we're done, we find that the total force on the lead line necessary to lift the 50,000 pound object is 15,194 pounds. I went ahead and rounded up to 15,193.8. And again, the 1.05 is derived from the 95% efficiency that we have and the 5% friction loss. All right, let's look at the shortcut method. Again, we're multiplying the per line force by efficiency to the nth power. There's our per line force, 12,500, times 1.05, our efficiency. And we take that 1.05 to the 4th power because there are 4 parts of line. When we do that multiplication, we find our required pull force is 15,193.8, just like the long method. There's one other mechanical advantage problem I want to show you. This one involves a block and tackle, and I saw a variation of this problem in a CSP study guide, and it's an example of how questions can be tricked up to make them more difficult. You got to interpret the question to get to what they're really looking for. And you wouldn't see something like this on a crane operator exam because they're more straightforward. They want to understand the crane operator's knowledge without requiring the crane operator to interpret what is being meant by a question and what the question's actually looking for. But let me go ahead and we'll take a look at this problem, and then I'll talk about the type of information, interpreting the information in the question to get at how to do the problem. Okay. We have a block and tackle consisting of 2 double blocks, and it's being used to lift a weight of 2 tons. What is the required braking strength of a manila rope to safely lift this load? Use a safety factor of 10 and 10% friction loss per line. A couple of things right out of the gate. It doesn't tell you how many parts line you're dealing with. It says 2 double blocks. We'll talk about that as I work through the solution to the problem. Also, it doesn't give you the pounds, it gives you the tons, so you've got to convert tons to pounds. Another little twist, little wrinkle that, again, I don't like the question. If I had the final call on the CSP exam and what questions went in and what questions were left out, I would want to leave this one out. Yeah, I might get voted down. It's usually done by committee, but I would vote against this question. I would like to see the writer of the question be a little bit more straightforward with what they're looking for. Again, they are looking for braking strength. That's the ultimate. It comes right out and tells you what is the braking strength of the manila rope that you would use with this block and tackle to safely lift the load. And you're using a safety factor of 10. That part's straightforward. Just it doesn't come right out and tell you how many parts of line or how many shivs. You've got to be able to interpret what all this means. Then you have to do the conversion from tons to pounds also. But let's just go ahead step by step and look at how I would solve this problem. There are 2 possible strategies you could use. One strategy requires the test taker to memorize a multiple variable formula, a formula that's not going to be given to you on the CSP exam. And there's 6 or 7 variables in that formula that you have to memorize and know what all the variables are for. So I wouldn't do it that way. I would calculate the amount of force on the lead line necessary to lift the load. Then I would multiply this figure by 10 to account for the safety factor. But how many parts of line do we have? We need to figure that out first. 2 double blocks means there is a fixed block or an upper block with 2 shivs and a traveling block or a lower block with 2 shivs. We have a total of 4 shivs, which is 4 parts of line. 4 shivs, 4 parts of line in this example. One thing the problem doesn't take into account, or there's some gray area here, which could leave the test taker fumbling around. Just because you have 4 sheaves doesn't mean you're going to have 4 parts of line. It is possible, especially with crane load blocks, to not use all 4 sheaves. You can set up the reeving and only use 2 parts of line. You can set up the reeving and use 3 parts of line. It's one thing we haven't talked about, and I really don't want to get into it in this unit because of time constraints, but you can have an odd number of parts of line. So again, this question leaves, you're guessing here. And the best guess is that, yeah, there are 4 sheaves, 4 parts of line. That's what we're going to go with. And in the study guide where I found a version of this question, that's what they did. They just assumed that you would automatically jump to 4 parts of line, which again is not a good assumption because there are other options that could come into play. Again, 4 parts of line in the problem. So we need to multiply the friction loss factor by the force per line value 4 times. But what is the force per line value? We get that by dividing the load weight by the number of sheaves or the number of parts of line. But before we do that, we have to convert tons to pounds. 1 U.S. ton equals 2,000 pounds. So 2 tons equals 4,000 pounds. We have 4,000 pounds, 4 parts of line. That gives us individual line value of 1,000 pounds before we account for friction loss. Again, divide load weight in pounds by number of parts of line. This gives the force per line before accounting for friction. And now we need to think about the friction part of the problem. This is asking us to assume a 10% friction loss per line. Because of a 10% friction loss, the pull force on each line is going to be 110% of the pull force if there wasn't any friction loss. The friction loss factor is 1.1. That's 110% converted to decimal form. 110% converted to decimal form is 1.1. That's our friction loss factor. And at this point, we could do the line-by-line cumulative method that I've shown you in the previous problems, but I'm going to go ahead and jump right to the shortcut method. Our force per line is 1,000 times our friction loss factor to the 4th power. And it's a 4th power because there are 4 parts of line. So this is our required pull force. When we do the math here, 1,000 times 1.1 to the 4th, 1,000 times 1.46 gives us a required pull force on the lead line of the block and tackle of 1,460 pounds. But they're asking us what is the breaking strength of a manila rope to safely lift this load using a safety factor of 10. So we need to take this 1,460 pound force and multiply by 10, which is the safety factor. Multiply the required line pull force by 10. When we do that, we've answered the problem. We need a manila rope with a breaking strength of 14,600 pounds in this situation. Again, that's the safety factor of 10 being considered. Again, 14,600 pounds is the minimum breaking strength to ensure a safety factor of 10. All right, well, that's it for the mechanical advantage video tutorial. Let me know if you have any questions, and I will see you in the next video.